Hi, everybody. It's Professor Mitchell, and today we're looking at section 7.6 on inverse trigonometric functions. So quite a bit of this section is going to be review from pre-calculus. So you'll remember at the beginning of this chapter, we reviewed one-to-one functions and the fact that one-to-one functions have inverses. Now, if you picture the graphs of your 6 trigonometric functions, for example, you see here the graph of y equals sine x, and I'm including the dash part of the graph. That is clearly not a one-to-one function because it fails the horizontal line test. So y equals sine x with its usual domain, all real numbers, is not a one-to-one function and therefore would not have an inverse. But if we restrict the domain of y equals sine x, and there are a bunch of different ways to do that, but this is the way that is traditionally agreed upon by everyone, to restrict the domain to the closed interval from negative pi over 2 to pi over 2, what you see here as the solid line, then that is now a one-to-one function, and it has an inverse. And what you see down here is the graph of that inverse function. We've taken this graph and reflected it across the line y equals x. Remember that the domain of a function becomes the range of the inverse function, and the range of the function becomes the domain of the inverse function. So y equals inverse sine of x, also known as y equals arc sine of x, has domain closed interval from -1 to 1, and the range is the closed interval from negative pi over 2 to pi over 2. And then you can do the same thing with the other 6 trigonometric functions. The traditional way of restricting the domain of y equals cosine x is to be between 0 and pi, which creates a one-to-one function. And the graph of y equals inverse cosine of x is shown here. It also has domain closed interval from -1 to 1, but the range is the closed interval from 0 to pi. And here are the graphs of all of the 6 inverse trigonometric functions. The ones here on the bottom are not going to be quite as important as the 3 that are on top, and you'll see why that is in a little bit. Okay. And so, for example, even I don't have the domain and the range of these 3, the inverse secant, the inverse cosecant, and the inverse cotangent. Even I don't have the domain and the range of those memorized all the time, especially not these 2. All right. Okay, so officially, the definition of the arc sine and arc cosine functions. Let me mention one other thing, which I always tell my pre-calculus students. I find this notation very unfortunate, and I think I may have even said this to you in section 7.1, because we use this -1 superscript to also mean exponent. This is not sine of x to the power -1, which would be the reciprocal of sine x. This function has absolutely nothing to do with the cosecant of x, all right? And so for that reason, sometimes I prefer the notation arc sine of x. But I'm seeing that notation used sort of less and less. Really, probably 90% of textbooks use this notation. So y equals inverse sine of x is the number in the closed interval from negative pi over 2 to pi over 2 for which the sine of y is equal to x. Remember that trick that we do with inverse functions where we reverse x and y to get back the original function. y equals the inverse cosine of x is the number in the interval from 0 to pi, the closed interval, for which the cosine of y is equal to x. Now, I have something in my pre-calculus class that I call the inverse trig function game. And it goes a little bit like this. I ask you, what is an inverse trigonometric function? The answer is an angle, all right? So notice it says y equals inverse sine of x is the number in this interval. Well, a lot of times you think of these numbers as angles. Radian measure angles, right? So I think it's very helpful to remember that what comes out of an inverse trigonometric function is an angle, all right? An angle is what goes into a regular trig function. It's what comes out of an inverse trig function. All right, now there are some useful identities that are going to actually help us, well, for one thing, eliminate the need to use inverse cosecant, inverse cotangent, and even inverse cosine as much as we normally would have to. So one identity, which I apologize, I don't actually have written out here, but this picture explains why the inverse cosine of x plus the inverse cosine of opposite x is equal to pi, because those two angles are supplementary. And the inverse sine of x and the inverse cosine of x are complementary angles. Therefore, the sum of those two functions is always pi over 2. And you'll see that again a little bit later. All right, the official definitions of the inverse tangent of x, inverse cotangent of x, inverse secant of x, inverse cosecant of x. I don't know if I should really read this to you. Maybe just give you an opportunity to pause the video and take some notes. Notice the sort of weird range of the inverse secant and the inverse cosecant. It's the range of the inverse secant function is the closed interval from 0 to pi, except for the number pi over 2. And similarly, the range of inverse cosecant of x is the closed interval from negative pi over 2 to pi over 2, except for the number 0. And there is a very good reason for that. All right, more pre-calculus review. This is just going over how to evaluate the inverse tangent function. So hopefully you had a pre-calculus instructor who encouraged you to memorize the values of tangent x, at least in the first quadrant. So you can see those values. Just imagine here, let me pull up my pen here for a second. Okay, so imagine first we're working with the regular trigonometric function. I guess I should call this a y. And then, excuse me, this window is not where I want it. Okay. And then over here would be the tangent of y. Okay. So if y is equal to pi over, well, let's start at pi over 6, because I usually go in increasing order from 0 to 1. The tangent of pi over 6 is √3 over 3. The tangent of pi over 4 is 1. And the tangent of pi over 3 is √3. And therefore, if you create the inverse function, it switches those x's and y's. The inverse tangent of √3 is now pi over 3. The inverse tangent of 1 is pi over 4, et cetera, et cetera. And notice that if the input of the inverse tangent function is negative, then that's going to give you an angle in quadrant 4. All right, because remember, the range of the inverse tangent function is the open interval from negative pi over 2 to pi over 2. All right, So let's get rid of, let's see. Oh, here we go. Okay, moving on. All right, just a little bit about y equals inverse secant of x. There are several logical choices for the left-hand branch of y equals inverse secant of x. Using choice A, which you see here, you get an identity inverse secant of x is equal to the inverse cosine of 1 over x, which is an identity that's used by many calculators. So that's the one that we'll go with. All right, finally time for an example, and this is definitely a pre-calc example. We haven't done a stitch of calculus yet. So let's switch over to the tablet and have a look at these examples. Okay, so I think I actually gave away the answer to letter A here just a couple minutes ago, the inverse tangent of √3. If you're really rusty on your inverse trig functions, then what you can do is ask yourself, what is an inverse trig function? It's an angle, right? So you can give this an angle sounding name like theta. And what that means is that the tangent of theta is equal to √3. So now you just have to ask yourself, what angle between negative pi over 2 and pi over 2 has a tangent of √3? The answer is pi over 3. And by all means, please, my hope is by the time you get to Calc 2 that you've got your unit circle memorized. But if you don't, then I would rather have you print out a unit circle and use it than to, get the problems wrong. All right. Okay. Next, we have the inverse cosine of negative √3 over 2. Give this an angle sounding name like alpha. And that means the cosine of alpha is negative √3 over 2. So now we have to find an angle between 0 and pi whose cosine is negative √3 over 2. Okay, now the negative can be a little tricky. So pretend for a second it just said √3 over 2. And by the way, hopefully you remember that wherever there is a √3 over 2, there is also a 1/2 when it comes to talking about the coordinates on the unit circle. Here's 1/2, and then here's √3 over 2 up here somewhere. Remember that cosine is the x coordinate. So if this was just regular old √3 over 2, we'd be talking about this angle, which is pi over 6. However, we are talking about negative √3 over 2, which means we're talking about the supplement of that angle, which is 5 pi over 6. So this mystery angle alpha is 5 pi over 6. Make sense? All right, next we have the inverse cosecant of 2. Give that an angle sounding name like beta. And that means that the cosecant of beta is 2. Well, I don't know about you, but I don't have a list of cosecant values memorized. The number one thing I remember about the cosecant is that it's the reciprocal of the sine, right? So if the cosecant of beta is 2, then that means the sine of beta is 1/2. And that must mean that beta is pi over 6. All right, and finally, that brings us to example 2. which is asking us to find the cotangent of the inverse sine of negative root 3 over 2. All right. I went back and forth a little bit on how I wanted to show this to you, and I ended up with, I'm going to show you the simpler way. And with that, you might be thinking, well, why would you show us the more complicated way? And the only reason I would consider it is because there may be a problem later on that can't be done the way that I'm about to show you. But no, you know what? Let's just burn that bridge when we get to it. How does that sound? All right. So really the simplest way to do this, because negative root 3 over 2 is one of those nice values, right? It comes from a nice angle, would be to just evaluate the inverse sine of negative root 3 over 2. The inverse sine of negative root 3 over 2 is negative pi over 3, right? Okay, now, well, let's see. I think it would be fair to use anything that we learned in pre-calc. One thing that you learned in pre-calc is that cotangent is an odd function, which means that the cotangent of negative pi over 3 is equal to negative cotangent pi over 3. And of course, we know that the cotangent is the reciprocal of the tangent. And we know that the tangent of pi over 3 is root 3. Okay, and now we come to one of my favorite questions when it comes to just sort of the day-to-day operations of Calc 2. Do I have to rationalize the denominator? Well, if we were in a face-to-face class and you were doing everything on paper, I would say I don't care. All right. However, your online homework might care. All right. So it might be a fun thing to experiment with. The first time you run into an answer, don't do this on a quiz. Do it in your homework. The first time that you have to put in an answer like 1 over root 3 or negative 1 over root 3, try putting it in just like that. See if it marks it wrong. I have a feeling that it might. And I'm sorry to say, I don't know if there is a way to turn off that requirement. So we may be stuck with it. Anyway, hopefully you understand that the rationalized denominator form of negative 1 over root 3 is negative root 3 over 3. All right, and that takes care of examples 1 and 2. All right, so now let's do some calculus. The derivative of y equals the inverse sine of u. So I'm giving you the chain rule version, which is always the more useful version. The derivative with respect to x of inverse sine u is equal to 1 over the square root of 1 minus u squared times du dx. And this is valid for absolute value of u less than 1, which happens to be the domain of the inverse sine of u. So that works out. Okay, and this is one of those things that I cannot resist proving to you. All right, I'm going to show you 2 other derivative formulas, and I'm not going to prove those, but that's because, well, for one thing, the proof is pretty similar to what I'm about to show you. So if you're interested, it might be a fun thing to play with. Okay, I'm going to go back to the tablet and I'm going to show you why is this derivative formula what it is. I am going to do the regular version, not the chain rule version. I mean, the chain rule always works the same way. So, okay, so this is the problem that I want to solve right now. If y is equal to the inverse sine of x, what is dy dx? So here's how that works. If y equals the inverse sine of x, well, then that means x is equal to the sine of y. And we still want to find dy dx. So that means implicit differentiation. So using implicit differentiation, we're going to differentiate both sides with respect to x. We have 1 equals the derivative with respect to x of sine y, that would be cosine y, times dy dx, right? Okay, well, I want to find dy dx, but whenever I find dy dx, if possible, I want to express it in terms of x. So what I am going to do now is I am going to divide both sides by cosine y. Okay, and that is going to give me 1 over cosine y, which is secant y, equals dy dx. And what was y again? Y was inverse sine of x. So here's what we have. We have dy dx is equal to the secant of the inverse sine of x. Now, I suppose I could leave it like that, but I'm not going to. All right. There is a way to express that function as what we call an algebraic function. An algebraic function involves nothing but addition, subtraction, multiplication, division, polynomials, radicals. It does not involve anything like e to the x, natural log x, any trig functions. Okay, so hopefully your pre-calc instructor, if I was your pre-calc instructor, I definitely showed you this, explained how to simplify an expression like this. Let me remind you how that works just in case you're a little rusty. What is an inverse trig function? It's an angle, I hear you shout. Yes, so let's let theta equal the inverse sine of x, which means that the sine of theta is equal to x, aka x over 1. So what I want to do is I want to write secant theta in terms of x. And the way that I'm going to do that is I'm going to draw a right triangle. Remember, some old hippies came around here tripping on acid? You don't. Some old hippies came around here tripping on acid, right? That tells me that if the sine of theta is equal to x over 1, let's label this angle theta, then the opposite side to angle theta is x, and the adjacent side, wait a minute, nope, I messed that up. It's SOH, not SOA. I thought that looked weird. Yeah, it's supposed to be hypotenuse. Okay, would be 1. We want to find the secant of theta. The secant of theta is the reciprocal of cosine theta. Cosine is adjacent over hypotenuse. That must mean that secant is hypotenuse over adjacent. So we need to write the adjacent side in terms of x. Remember how this works? Using the Pythagorean theorem, the adjacent squared plus x squared is equal to 1 squared. That means that the adjacent squared is equal to 1 minus x squared, and that means that the adjacent is the square root of 1 minus x squared. See where this is going? Okay, so the secant of theta is the hypotenuse, which is 1 over the adjacent, which is the square root of 1 minus x squared. So remember, dy dx was the secant of inverse sine x, which is secant theta. This thing here is dy dx. Ta-da! All right, and of course you don't have to memorize these formulas, at least not if you're my student. You just have to have them written down on whatever notes you're going to be using when you take your quiz or your exam. All right, so that's the derivative of inverse sine u. You can use similar technique to prove the derivative formula for inverse tangent u, which is right here. And you can even do the derivative of inverse secant u. Let me just point out something kind of interesting about this formula. It has a square root of u in it. Really nice challenge would be to try to derive this formula the way that I just showed you with y equals inverse sine of x. See if you can figure out why that u has to be an absolute value. That's a fun challenge. Here is an explanation for why it at least makes sense that it should be like that. So this picture is showing you that the slope of the curve y equals inverse sine a secant of x is positive for both x less than -1 and x greater than 1. So that means that the derivative always has to be positive. And unless this u is an absolute value, then that won't happen. All right, by putting the u in absolute value, you get that this derivative always gives you a positive number. All right, now you might be thinking, oh my gosh, we're going to have 6 totally different formulas for the derivatives of the inverse trig functions. Well, it turns out, no, you don't. So I was talking about one of these identities earlier. I was talking about the fact that inverse sine x plus inverse cosine of x is equal to pi over 2. Well, it turns out that the same kind of thing is true for inverse tangent, inverse cotangent, and also for inverse secant, inverse cosecant. So when I go to find the derivative of inverse cosine of x, well, I can just take the derivative of this expression here. Of course, the derivative of pi over 2 is 0. So this means that the derivative of inverse cosine of x is just going to be the opposite of the derivative of inverse sine x. And the same thing is true for all the other co-functions. So nice pattern here. Really focus on the main 3 being, get my pen here. The inverse sine, I thought I had turned on my pen. Okay. Well, the inverse tangent, the inverse secant, and darn it, I've got this window that pops up. I guess I have to move it. It's right in the way. Okay, there we go. Now I can circle this. And then notice that I'm using a touchpad mouse, which is why I can't really draw on the screen very well. All right. Notice that the derivative formula for inverse cosine is just the opposite of the derivative formula for inverse sine. Same thing for inverse cotangent, inverse tangent, and for inverse cosecant, inverse secant. All right. Would really be helpful if you had to memorize anything, which of course you don't, but it even makes your note taking a little easier, I think.